Good afternoon, everybody. My name is Ken Grobe. I'm Director of Embedded Technology with ELMA Electronics. Great overview from Nigel about the building blocks and how systems can be put together. So, as Nigel introduced, MOSA, sometimes we think of it as modular standards, but actually it's a modular open system approach. And this is an approach directed by the tri-service memo that's been updated twice, as Nigel pointed out, that is helping us to standardize our interface and deliver technology more rapidly at better cost as systems are implemented. So moving on. Today, I'd like to cover where MOSA is being applied, some of the challenges that have driven the open standards or are driving the open standards and why, how SOSA affects the architecture of the systems and the adoptive standards, a little bit about development and deployment. You have to start somewhere when you're putting a system together, and then ultimately it needs to lead towards a deployment platform which is ruggedized. In Nigel's RF chain, he is explaining and showing the architecture for RF systems. Wanted to talk a little bit about MORA, which is one of the standards referenced by SOSA and CMOSS to put systems together that use RF elements. Also touch on chassis and system management, which is a capability required by SOSA for managing systems, and chassis management for managing PICs and things that are in the system. Hardware architecture, touch on that a little bit about AI and how you can be enabled to put elements of the system together for AI applications. A brief look at a CMOSS case study, and then a few of the ecosystem building blocks that are available. So where will MOSA be used? It's being mandated. Obviously, it can be used across the tri-services as mandated by the DoD. And what we're seeing is that it'll be used in many places, at embedded systems at the edge, in sensors, since SOSA stands for Sensor Open System Architecture. These reference models are being developed to support different modalities of use. Modalities like signal intelligence, communications, EW, and ISR, to name a few. This is not the only ones, but these are some of the primary modalities. So if we look at challenges and take a look inside a vehicle and look at what needs to get done, we see on the right kind of a messy picture of a bunch of boxes in a vehicle with interconnecting cables. And what we see is as the warfighters' use cases change and the need for the DoD evolves, what we need to do is develop mission capabilities that span these different modalities, including communications, EW, radar, and SIG-INT. And sometimes one would want to modularize this capability and be able to sort of mix and match it within a chassis, which really can't be done today. Although as we go forward, multiple modality systems will be possible, which gives us a way to address size, weight, and power and the space claims within the platforms. So we need to do this because threat posture changes in the world, and it requires us to make new equipment, modernize that hardware, and get it out to the warfighter in a timely manner. Also, when you look at this, you've got a complexity of different types of, let's say, functions that need to be maintained. You have training around that, and you have upgrades. So where standardization can take place, it helps reduce this cognitive load on the user and make it easier to actually implement it and maintain the systems. Sorry, my button is a little bit stuck. Further, if we look at the space claim, picture on the right shows a complement of systems that will be implemented in the vehicle. What's occurred over time is that without standardizations being driven down from the top, one tends to get into an environment where you have stovepipe systems, where there's expertise from certain suppliers around quite good hardware that gets implemented, but it becomes sort of implemented up a vertical. So interoperability across that equipment may be more difficult. Leaving industry develop different components that could modernize the equipment is not really possible. And then you run into size issues where you've got a constraint in a platform where you only have so much space. So this leads you to competition within the platform where you may not get the capability that you need because you don't have any room to put it anymore. So these are things that are sort of pressing on the different corners of the solution and the implementation that add complexity, and then that can lead to additional cost. So one says, what is a better way that we can achieve these things? And this is the goal of the modular open system approach. So if we think about deployment and development, what we need to do is start on the left with a development capability and then move that capability to the right to a deployment environment. So this is what we're reflecting in this diagram. Around that, we sort of have these vertical technologies that are pointed to by the standards that let us address different elements of the system. So the top one is something called MORA, or Modular Open Radio Architecture. The middle is a stack of technologies that would be available from NVIDIA that would help folks use this technology to implement AI capabilities. And at the bottom, what we have is a set of architectural standards that implement an architectural called systems and chassis management that allow one to interface with the system and to also control it. So if we look at this, and Nigel gave us a spoke that showed different activities in his presentation. Here, we're showing technologies and standards in a stack and how those standards and implemented capabilities can form a sort of hierarchy to get you to the overall sensor capability. At the bottom, what we have is a standard called OpenVPX that describes the hardware. And the next thing that one would need to do is take that OpenVPX standard and manifest some sort of environment that allows you to develop. And that would be done in the gold block with development systems. And of course, these would be produced by multiple manufacturers. I'm looking today at what ELMA is offering to the market. So to the left, we have that black box. It's a compact frame that includes a backplane and a power supply. It also includes a chassis manager that gives us the capability to develop and combine PICs into a system. On top of that, other technologies that could be incorporated would be available from companies like NVIDIA with implementations in the marketplace of GPGPUs that allow you to apply this to form AI capability. And sitting on top of that is something called MORA, which is an architecture for RF. And along with that, there's tools and reference platforms that can enable that capability within a system to handle the RF. Lastly, you get to what is really the bottom line, the customer application and the sensor modality, where tons of work is being done in that blue block to implement the overall system capability, which is the end game. So taking a look at these quickly, one by one, we see what SOSA has done. There's a lot of talk about the hardware aspects of SOSA in normalizing the hardware, which is completely necessary. But SOSA is doing other things that doesn't usually get as discussed as much, where we see work being done in the software infrastructure to promote interoperability and portability. One thing SOSA does is implement the runtime environment, or define the runtime environment, I should say. And it's supporting things like FACE OSS, which is an example of reuse, where FACE has been around prior to SOSA, which provides an environment for operating a system or building a system. It also defines containers, which allow one to abstract software modules to promote interoperability through container definitions like Docker and Kubernetes. Further, it gives us a recipe for the virtual machine architecture that should be used and guidance on how to implement that. All of this helps to promote interoperability. Then when we looked at next step, SOSA also points to capabilities called system and task management, where the system manager is responsible for managing modules and infrastructure within a SOSA sensor. This breaks down into a bunch of APIs that need to be implemented, and it's also related to another function called task management, which is what actually coordinates the operations of the sensor. Lastly, we've got Modular Open Radio Architecture, which is a standard that's pointed to by CMOSS, CMOSS being C5ISI Modular Open Suite of Standards. And this defines how the signal layers should be implemented, and it's actually a requirement for things that will be CMOSS aligned or ultimately CMOSS compliant. So looking at challenges again, to make products be able to be developed that are interoperable and to develop them quickly, we need to have a definition that is accomplished through MORA. Again, MORA is Modular Open Radio Architecture. And what it does is decouple the RF hardware and signal processing chains. It actually decomposes it into components that are well-defined. So manufacturers have a common recipe to implement these capabilities. And it allows you to grow on existing efforts and to take that forward into new designs. So we look at the building blocks. What we see is elements like a software-defined radio that's picking up its data from the high-speed data bus, or what's called the MORA low latency bus, and then communications for control through something called the VDB, or Victory Data Bus. And as we go around the buses that implement the data flows within the system, what we also see is other functionality, a processor, a mission processor, and that implements parts of the MORA architecture, radio heads and antennas and power amplifiers, and below that RF distribution devices. So MORA decomposes the radio system into high-level components that enable sharing. And when you're considering software-defined radios, what's needed there is flexibility to run things like different waveforms for both communications and EW. MORA lets all these things happen in a modular way, and it allows one to be able to build on work and then potentially reuse that work to keep technology refresh, let's say, possible, making it faster, that allows one to innovate new capabilities faster. If we look at how that decomposes, a MORA-ready system that has elements of the MORA standard already implemented is possible. And this shows an example of what we call a MORA-ready development platform. In this case, we've got a processor by Abaco for mission computing. This could also be a processor from Concurrent that operates in a similar way. We support both. We have a switch, and then we have a transceiver. The transceiver implements or looks like a MORA device, which is actually a software-defined radio, and it communicates over Ethernet, both in the control and data planes. So we have MORA signal domains taking place in the RF receiver. We have a single board computer that implements MORA processing as a processor resource. And we have a high-speed switch that does the data flow networking that's required between devices within a particular system. To the right, what we've got is profiles. And as Nigel mentioned before, these profiles were not defined or standardized, but made it practically impossible to have interoperability because the I/O mapping would be different. Today, that mapping is specified. So manufacturers need to use these profiles that are shown. The one in the middle here is the one for PNT. The one to the right is the switch. The one to the left of the first slot is the payload profile, and then the IO-SBC profile. This allows manufacturers to make interoperable PICs and then ultimately allow them to be ported to the MORA standard to be able to handle RF. So lastly, how do you attack the software? Now the ecosystem is addressing ports to MORA with tool sets from a company we are partnered with called Science Innovations. What we're doing here is taking the different elements of a MORA tool suite and utilizing that to integrate it into off-the-shelf PICs to make a system MORA ready. The tools that you would get would be MORA Explorer, which is like a terminal that allows you to interface with MORA functionality in a system to be able to give it controls and to also to be able to do things like review and display information that's in the MORA, let's say, API. Secondly, one needs to manage the MORA resources through something called the MORA signal resource profile. And this is done with a tool called an MSRP generator. This allows you to describe an RF device and to give it a profile so then that it can be then communicated with in the context of using MORA. In the middle on the right side, we see a block that's equivalent to the SDR, and there are certain functions that must be put into that. And these are implemented with what we call Helix Core and Helix Client Core to implement and stand up the MORA capability within a device. So these tools across the board then allow one to quickly leverage existing software to implement MORA capability within a system that must use RF devices. So now I'd like to show a quick video that shows a little bit more about how this works. And I think we'll tee that up from Marvin.
Introducing ELMA's MORA Ready Development Platform, MRDP. The MRDP is a turnkey 3U-VPX development platform, pre-integrated with plug-in cards and software, aligned to SOSA. This robust system allows developers to instantly begin creating or integrating applications for MORA-focused mission-critical defense projects. At its core, the MRDP features ELMA's 6-slot open VPX backplane, fully aligned with SOSA and CMOSS profiles. The standard configuration includes plug-in cards such as an Abaco compute-intensive processor, an interface concept Ethernet switch, and an EPIC transceiver, all integrated and ready to use out of the box. What sets the MRDP apart is its pre-integrated Science Innovations Helix tool suite. This comprehensive software package includes MORA Explorer and MSRP Generator, allowing developers to immediately visualize, control, and configure MORA resources. This integration can save weeks or even months in development time. The MRDP isn't just for lab use. Its configuration can seamlessly transfer to ELMA's deployable platforms, such as our CMFF Save Chassis or SOSA-aligned half-ATR. This ensures a smooth transition from development to field deployment.
Thank you, Mark. So, you just keep this moving. Let me touch briefly then on two other technologies that are in our stack. AI application and making systems, say, capable to use AI elements, and that would be comprised of GPGPUs and CPUs, requires an architecture that lets these high-speed communications take place. As Nigel mentioned before, what we've got is the need for PCIe to take place across the expansion plane. And what we can actually do is put multiple instances of GPGPUs in a single system if needed. So to accomplish that, we need to be able to connect a processor, which has an Intel SBC, or is implemented with an Intel SBC, and then connect that up to GPGPUs. Here we're showing two instances of that through standard profiles that are available in OpenVPX and defined within the SOSA specification. If you need a higher performance implementation, you need to have a wider data path. And to do that, there's a secondary slot profile that expands the width of the data path to by 16 between two payload slots that allows one to use the widest possible communications pipe between the GPGPU and the processor. So what we're doing at ELMA is putting all that capability into a backplane that we call backplane suited for AI development or AI ready. And what we're showing in these two slots are standard payload profiles that are implemented connected to an IO-SBC, and then the possibility to add a compute-intensive SBC along with a high bandwidth GPGPU that uses the wider connection. This may be manifested in a different configuration than the ultimate deployment platform, but this allows one to quickly be able to mix and match devices like RF devices against GPGPUs and CPUs against GPGPUs for compute-intensive applications to perform development. Some of the processors or GPGPUs rather that you could get from our partner ISO include the Ampere GPGPU with wide input. This is up to by 16. It can be used by 4, by 8, or by 16. And then also system on module capable GPGPUs from the Orin, AGX Orin system on module that implements the Ampere architecture and an ARM processor cores within that device. So both of these types of devices can be plugged into slots that are described by standard profiles and then stood up against CPUs that can drive them. So the next component of technology I'd like to talk about is system and chassis management implementation and the tools that can be used to develop that. That's pointed to by this architectural diagram that's found in the SOSA specification. In this, we've got two types of interfaces, two types of interfaces, the in-band and the out-of-band. But before we get to that, we look again at standardization that's being promoted by SOSA for the RTE being the runtime environment. And here, different configurations of the RTEs are described. The one that's interesting today that's being looked at quite a bit is container RTE that allows us to modularize software using container architecture in the runtime environment. Further, you might need to use virtual machines, and the virtual machine RTE is also defined within SOSA, including examples of the hypervisor. What this leads to is more like an app store sort of concept around SOSA software, where software will be modular and much easier to operate out of the box than if these things are left open and not defined. So this helps with interoperability and portability. When we look at system management, the specification defines APIs for both the in-band and the out-of-band. The out-of-band interface communicates with the SOSA hardware or SOSA-aligned hardware that's within the system, and it talks over something called IPMB. The in-band typically talks over network interfaces, and there's a host of functions that are defined in the in-band interface. This is a RESTful interface that communicates over a network from the hardware elements to the system manager, and also between the system modules or the aligned software modules. If we break this down, the system management is implemented across a bunch of interactions, and we see them defined in this chart. We have interactions for the system manager, the chassis manager, interactions for the PICs, which in many cases are processors or they're plug-in cards that have other hardware functionality, and then the runtime environment. So a number of APIs. What this affords is the ability to modularize the software and to offer building blocks that can be reused, which is beginning to occur. So in this way, one can implement the agents and the clients and server software modules that are necessary to implement system management. As an example of that, ELMA has been working with Science Innovations to develop a system manager user interface that does things like show sensor status, sensor state and mode, and bit configuration and use, so you can be able to control these things. As time goes on, more of the software will become available and supported by the ecosystem, and it's ELMA's goal to be able to release an initial product within the year. So wrapping up with a case study, over the last 5 years, actually more than that, the Army's been working on adopting standards that'll get them to this point, which is called the CMOSS mounted form factor. ELMA has participated in this. We've participated in it with other partners in the ecosystem like Concurrent develop a capability, in this case a chassis that's aligned with SAVE, that implements the standards that are prescribed by the Army if one would be compliant with CMOSS. What this does is provide a standardized space claim for the vehicle and a platform where people can use, or developers can make system architecture like the ones that we talked about in the beginning and are a topic of this presentation, including EW, communications, mission computing, etc., and to be able to quickly get that into the field. CMFF will be implemented by multiple manufacturers to give a choice and to help manage the cost. So there will be a number of folks in the ecosystem who will actually build to this standard. So last couple slides, looking at the architecture of a system that uses a SDR and an SBC. The items in blue show where MORA is utilized within an RF device. And over here, what we're looking at is where system management would be used in a processor. In the middle, we're looking at the switch and the data flows between them. And at the bottom, where we have chassis management implemented in the system to provide functions or provide the capability to provide chassis-related functions. So building blocks to implement these capabilities are now becoming available, as Nigel pointed out, with a great wrap-up from available hardware. We've got multiple people making development systems, deployment chassis, PNT cards, network switches, transceivers and SDRs, and a number of folks making power supplies. Recently at the Plug Fest, we had a number of the suppliers building these things available, plugging and playing them within chassis that were available at the Plug Fest to make sure that they interoperate. And I think there were 4, maybe 5 different companies making power supplies that were plugging them in and out and seeing good results during that event. So in wrapping up, system packaging for deployable solutions are the ultimate goal from ELMA's point of view. We have 2 systems that are aligned to SOSA and CMOSS today that implement the SAVE standard in the top one, which is a CMFF system that's 7 slots. And below that, we have a top loads 6 or 7 slot solution that implements connectorization that's defined by SOSA, addressing chassis management and an open platform. So that's all I have. Thank you for being able to speak about the MOSA approach today.